Welcome to Breadboarding. This is video 48 in the Breadboard 8088 PC series, and this is part 3 of the CGA video controller. So in the Breadboard PC series, what we've been doing is building out a basic Intel 8088 computer which had a 7-segment display and keypad. Then we got a basic floppy disk PC where we've actually built a monochrome display adapter video controller, and we've also managed to get a floppy disk controller working, booting early versions of MS-DOS, and we've been looking at MS-DOS 3.3.0. The next stage of the project, we've already built out the IDE disk controller and able to boot MS-DOS off the hard disk, and as part of building out the CGA Colour Graphics video controller, this should allow us to run an early version of Microsoft Windows. So first let's take a look at the current Breadboard PC, and we'll look at the MDA video controller and look at what differences are going to be between MDA and CGA. So this is the Breadboard PC. You can see the keypad and the LED display from the very first stage in the project here. This was similar to the original Nanocomp 6809 that built out a project about 2 years ago. And we've also then got the hard disk and the floppy disk over here. And just around here, this is the monochrome display adapter. So buried underneath here, we do have a VGA 15-pin connector. We've got a dual port video RAM down here. So this only needs to be about 4K in size, and unfortunately dual port video RAM is difficult to come by these days, and the 16K that we need isn't really practical to use these chips, so you're going to be using a faster 32K static RAM chip. Then we've got the CRTC video controller chip here, and there's also then a VGA digital analog converter palette chip over here. So a number of these things are going to be common between the two designs, and this is actually made on 4 breadboards here. So we've got 1, 2, 3, 4 breadboards. I suspect for the CGA we're going to need to perhaps add another one down the bottom here somewhere, but we should be able to fit it on 5 breadboards. So let's just power this on and check that it's still working, and we're going to have a look at the test utility that we're going to be looking at for checking out that the video cards are working properly. You can see it comes up with the Nanocomp monitor here, and we're just going to boot into the BIOS. You can see here the power on self-test information for the BIOS here coming up. And you might have even seen the LED for the hard disk flashing down the bottom left hand side here. So that's into MS-DOS 3. Let's just make that full screen now. All we're going to do is look at the CT utility. So this is being built by Emil, so thanks very much for him for this. And there's a couple of things we can do with this. The first one, we're just going to do test mode. So this is going to detect the various hardware that we've got. And you'll see here that it doesn't detect a CGA 6845 card, so none, but we do have a mono card, the MDA card. So that's what we'd expect because we do actually have this working. And if we do various video modes, you'll see that some of these early video modes are supposed to be 40 characters wide. And you'll see that with the monochrome display adapter, we don't get any colours. We've just got variations of intensities of green. And if we then do another video mode, again we get the same characters, and again similar sort of thing. And finally, if we do the CT7, which is the monochrome display adapter mode, you can see that there we get the various different attributes of blinking and underlined text. Should note that it's only the monochrome display adapter can actually do underlined text in text modes. So we've got it working, and we just need to then, when we add the CGA card, we're going to need to run through these tests, and there's a number of tests that it will go through to draw various graphics and test out the 40 character wide and 80 character wide video modes. Now in the previous video, which I'll include a link at the top and there'll also be links down in the description below, I went through the diagrams from the IBM technical guide, which included the schematic diagrams. I went in that in some detail. I'm not going to go through them now, but we're going to be referencing some of the information in here as we go through the KiCad CGA diagrams and also the updates we're going to make to the Breadboard PC schematic in KiCad. So you can see here the various diagrams. I've gone through and annotated quite a lot of it to try and understand what's going on. I'm not going to speak too much about it because it's much easier to look at the CGA KiCad project that I discussed in the previous video. And there's bits we're dropping the composite video outputs requirements. So let's take a look at the KiCad CGA project that I referenced in the previous video. So this has been produced to generate a PCB with a hardware compatible CGA card. So if you have a look, I've gone through and annotated quite a few of the sections. I'm not going to go through these comments at this point in time. As we come to do all the various programming rules for the programmable logic devices, which are going to implement a lot of this stuff, then we'll be referencing back to these diagrams as we do those PLD rules. So this is where we've got the cathode ray tube controller chip, we've got a number of buffers and latches, and then there's the dynamic video RAM. Now, by using static video RAM, we can avoid a lot of the complexities of dynamic RAM refreshing, so we're going to do that. One of the more confusing bits of the CGA video card is that what it actually does is has two graphics serializer shift registers. Now normally what happens is if you have your character generator ROM here, we feed the raster rows for each character into a shift register here, and this produces the character generator dots output. Now, I'm not quite sure why the CGA card did this. Perhaps it's because the dynamic RAM it was using was too slow to be able to access it any faster than this. But what this actually does is takes the output from the character latch and the attribute latch, which are used in text modes, and then feed these into these two shift registers. And if you'll see, the inputs to the shift registers have combinations between the attribute bits, so you can see AT0 and AT1 alternating between the two, and then the character bits as well, so you've got CC0, CC1, CC2. So that's a little confusing, and it's taken a little while to unpick all of this. Needless to say, we don't actually need to do things like this. We're not trying to produce a completely hardware and timing compatible CGA card. We just want a CGA card that's software compatible and produces VGA compatible output, so we can use it with modern display equipment and video capture devices. At the top here we've got our color register. So this is a new register that the MDA card doesn't have, and this basically allows us to define the red, green, blue intensity for the overscan areas and also used for the backgrounds. And this also allows us to select between the color palettes used in the 4-color graphics mode, and in fact also this overscan color is also used for the foreground color in the high resolution 640 by 200 graphics mode. Now, in addition to these serializers that produce these two outputs, C0 and C1, we've then got two multiplexers down the bottom here, and these multiplexers are controlled by two signals known as MUX A and MUX B. Now we'll go and see where those signals come from, but basically two multiplexer signals really determine whether the color we're showing is for foreground text, background text. We've actually got the 4-color graphics, what the various output values of C0 and C1, and in fact also it makes up the blue signal. So we only have two outputs from above here. We need 3 for the colours, and in fact the blue signal is actually generated depending on various other settings. You see the cell blue coming in here. And finally the graphics overscan, this basically provides the colour around the active area of the display, which on CRTs was more of an issue, not really going to be a problem with an LCD monitor. And there's also another signal here, STR. When STR is low, then we get output from here based on the multiplexer values. When STR is high, we just get black. And this is important when we come to the high-res graphics mode, because STR will go high when there's black going on there, and it will show the graphics overscan color when we want the foreground color. And it's all quite confusing to try and unpick all this stuff. Then there's a clock circuit here, and we're not going to worry too much about the clock circuit because we already have a working one, and we're going to primarily use in the clock timing that we used for the monochrome display adapter card. And then there's a couple of outputs here. This is the address decoding. So there's the address decoding for the I/O ports down here, and there's also the data gate enabled. This actually enables the buffer which goes onto the main computer address bus. And so this data gate is actually determined here. And again, I'm not going to go into the details of these at the moment, but as we go and do the rules for these various PLDs that control all of these devices, then we'll need to refer back to this information here. This is probably the most complicated bit. This is where the control register here, so this is the control register that provides a lot of the signals to determine whether we're running in 80 column mode in alphanumeric or 40 column mode. So high res being true means we're in 80 column mode, high res low means we're in 40 column mode. Whether we're selecting graphics, now in fact if we're in any graphics mode, then the graphics signal will be high, and if we're using the 640 by 200 black and white graphics, which is not quite correct because the foreground colour is actually determined by the colour latch. So in fact this mode, if this one is high and this one is high, we're in high res graphics. If this one's low, we're in the R4 colour graphics. And there's also the blink enable, and this controls in text modes. If blink enable is enabled, then the upper bit of the attribute for the background is used to enable blink rather than allowing for high intensity background colours. So if enable blink is set to 0, then we actually get 16 background colours. If it's enabled, then you only get 8 background colours, but you can have blinking video. And we can see down here that the cell blue here is in the 4-colour mode. Depending on which colour set we have enabled, then really the blue will either be enabled or disabled depending on the colour palette which is selected. The outputs here, we mentioned previously the composite video modes which were compatible with TV outputs needed to modify the horizontal sync and vertical sync signals to make them compatible with TVs. We don't need to worry about that. There's a few delays and things going on here, and there's also the one bit here is the video enable output of the control register is only actually used in this one bit here, and what this does is actually clears the shift registers. So what we need to do is to make sure that the circumstances under which this logic is triggered, so this basically happens for 1 character clock cycle when the display enable indicates that there's no valid output, then what this will do is clear the shift registers and will also take into account the video enable. So if video enable is set to 0, then in fact the shift registers will be zeroed and you won't get any output. Then finally, the only bit of really significance on this, which is the bus connections, we just need to worry about this buffer here. And this buffer we're putting in so we don't actually overload the rest of the Breadboard PC data bus. And there's some logic here to determine which direction we're going. And we can see here that the data gate signal from earlier on in a couple of slides before, that this is the chip enable for this to determine whether the buffer is enabled or not. So based on all this information, what I've now managed to do is update the KiCad diagram for the main Breadboard PC. If we just go back into the Breadboard PC KiCad diagram, you can see over here it's now getting very busy, but I should just say that the reason why I use KiCad in this particular way is you'll see over here where we have the monochrome display adapter card that I put the power rails in. So this is effectively 1 breadboard, 2, 3, 4 breadboards. Generally I try and keep the layouts in here as close to the physical layout as possible. It's not always possible, but most of the time I do manage to do this. Now one of the other things I do, which is a little bit contrary to the way how most people use KiCad, is what I've actually done is gone and modify the chip symbols here, and I've made the chip symbols actually match their physical pin layouts. Probably the easiest way to look at this is if we look at one of these sort of buffer chips perhaps. So if we look at the 74LS574 latch, what this has is 8 inputs, 8 outputs. There is a clock or latch and an output enable. Now if we actually go into KiCad and look at the standard 574 symbol, so if you look at the 574 symbol here, What you can see is that most of the KiCad symbols are arranged to make them logically consistent, so that you tend to have all the inputs on one side, the outputs on the other side, for example, and then the power tends to go at the top and the bottom. And that makes for nice neat diagrams, but it doesn't really help to lay things out on the breadboard. And so what I've ended up doing is I've taken these standard ones and I've added them into this breadboarding group, and in this particular case you can see that what I've done is I've reordered it so that in fact it has all the pins in the physical sequence, so 1 to 10, 11 to 20. Now by doing that, what it means is that when I'm actually laying out the diagrams in KiCad in the schematic, it's very close to what the physical layout is going to be. And obviously when you find that you've put all of the inputs on one side and they need to be connected over to something on the other side here, what that indicates, you can rotate the chip perhaps to say, right, if we rotate the chip we can simplify the layout. So all of the chips in the breadboarding group have generally had this modification done, and I know that there are some people who've used the PCB designer to do breadboard layouts, but really I think that's an extra step too far. What this enables me to do is to basically do the breadboard physical layout pretty much in KiCad in this particular way. So you'll see there's certain areas of the board which are busier than others, but by making, for example, the pins line up here between the dual port RAM and the address outputs of the cathode ray tube controller, you can see that you can simplify the layouts a little. There's also the bus signals as well going around here, and you'll notice that in a lot of my designs I use the DuPont cables with 8-way shells for the pins, and this simplifies wiring up all the bus signals. So what I've done is I've taken the MDA video controller and I've made a copy of it and I've moved it down here. So now we have an MDA video controller and a CGA video controller. One of the key things to note is that MDA and CGA video cards can coexist in the same computer at the same time. And in fact, that CT utility that I showed you earlier and the mode command in DOS will actually allow you to switch the active video card between MDA and CGA. And so it would be possible to do certain debugging and things like that using the MDA card if you were doing something with CGA, for example. So I'm just going to pick out some of the key highlights and changes here over the previous one. So over on the left hand side here, this is our VGA 15-pin subminiature D connector. And the main change over the previous diagram is that now we're no longer got a dual port video RAM chip here. What we've actually got is a 32K high speed static RAM. This is a 15 nanosecond access time, so it's very fast, much faster than the original dynamic RAM that the CGA card would have had. I believe from the schematic that it may have been 400 nanosecond dynamic RAM parts, which is probably why they had some of the more complicated shift register and output stages. But what I have had to do, because we don't have dual port video RAM that has 2 lots of address lines and 2 lots of data lines, what we've now got is a buffer here for the data. We've then actually got 2 lots of latches. So we've got the CPU address latches here, and we've also got then some PLDs to provide sort of multiplex latches for the output from the CRTC. Because we need to switch some of the address lines around between on which video mode we're in, I'm going to use these programmable logic devices to do this, just because it makes the wiring things up easier. Basically we need to include the RA1 signal at the higher end of the video address range when we were running in the graphics modes. The main area of change around the video RAM is here. So I need to make some changes here for the I/O port decoder. So this is similar to the MDA one, apart from now change a lot of the signals to be CGA, otherwise we're getting conflicts, and the ports and the rules for this will need to be updated to the CGA port ranges. There's also another PLD here for handling a lot of the timing signals for some of the chips down here. We've added a data bus buffer here, which the original MDA card didn't have, but that just means that we won't be stressing out the rest of the Breadboard PC data buffer. There's an extra latch in here, and this latch basically enables us to be able to do the high resolution black and white graphics mode. What this basically does is takes the data out of the video RAM and allows to feed it directly into the shift register over here. Normally it's the data output coming out of the character generator ROM that goes into that shift register, and all we're doing now is we're controlling the output enable of the character generator ROM. Rather than being hardwired to always be on, is now controlled to this chip over here. So when our graphics latch is actually writing to the shift register here, this is turned off, and when we're not in the high-res graphics mode, then the character generator ROM sends the data to here. The other main changes I've made is the attribute latch is now being changed into a latch stroke multiplexer. So rather than using a straight latch chip like I did in the previous ones, we now have the data input going into here for the attributes. This is the foreground and background colors, for example. And rather than output all the foreground and background colors into over here to then have to sort out, what I've in fact done is output the red, green, blue intensity signal out of here for either the foreground or the background color based on the shift register dots that are coming out of here. So where we have the shift register dots coming out for either the foreground or background color, then rather than having to actually output all the foreground and all the backgrounds, we're only outputting the relevant one at the particular time. And this is also then able to take into account two of the clock signals that we actually have. So these are counting, there's 4 counts within a given character clock given by QC and QB clock outputs. This basically means we can output the 4 color C0 and C1 colors correctly. So the bit 7 and bit 6 will be C1 and C0 for the first bit, then second, third, and then fourth bits there. So this has actually simplified some of the output and has avoided needing to have all of the complexity from the original design of all the shift registers. So effectively by doing this, we've eliminated these 2 shift registers here, and in fact the one chip now is doing all the multiplexing that is required for the attributes. So these 2 chips have been merged down into one PLD. Now some other changes around here. What we're actually outputting to the video digital analog converter is the colors for red, green, blue intensity. There's also another signal here, and what we're going to do is to allow this to output either grayscale or colors. Now the original CGA card, if plugged into a composite monitor, would actually have a black and white signal and configuration, and that would actually turn off the color burst signals, so it would actually just do shades of grey. And although if you plugged in a color CGA monitor it wouldn't pay any attention to the black and white side of things, I thought it might be interesting to enable the black and white grayscale mode. So if this P4 output and the BW input here that we can see here, if that's high, then in fact it will set that P4 and it should allow us then to have a grayscale configuration in the video DAC over here. So other than that, I've shuffled 1 or 2 things around to the blinking PLD for handling the blink clocks and things. I've just moved from over here down to here, so we've got a bit more space. But other than that, I'm hopeful that we should be able to do this whole design using 1, 2, 3, 4, 5, 6, in fact, breadboards. So the previous MDA just had the 4 breadboards here, but because we need these buffers and latches for the single port video RAM, then that's really why we've had to add this extra layer on. And we've also added a data buffer to the rest of the data bus to prevent any overloading of the data bus. So I've updated the diagram that I used in the video 1 of the CGA video controller. So this was based on the original MDA card, and what I've done is I've updated this, and where there have been changes then things are in orange. The biggest change really is the video RAM is now a static RAM single port. We now need to add buffers and latches around this RAM. We have to change the I/O port decoder to change the addresses. The character generator ROM is going to be different because it's going to have different character sets. It's going to have a 5-bit wide character and a 7-bit wide character, the two options that CGA had, and those can be switched between using a link on the board. Because we're doing double scanned, so the 200 lines is being output as 400 lines of VGA, then in fact the row address or raster address 0 line is being ignored and we're only using 1 to 3. So this means we've got the characters made up of 8 rows, and we've also then had to adjust the addresses that are being fed into the character generator as well. We've got the CGA control port and status registers. So the control port is different, has different signals from the MDA. Now the color output here, the attributes, it's changed slightly, as I showed that we've now got a PLD here rather than a latch, and this just allows me to simplify things a little by outputting only the current selected color. And then the blink PLD is very similar. There's again similar changes to the attribute multiplexer and the video output too, and we'll be going through the configuration rules, those in later videos as we actually plug those in and program them. Then the CGA Colour register is a new register for CGA. This provides the red, green, blue intensity for the overscan, which is the area outside of the active text area, particularly on the TVs and cathode ray tubes, and then also provides the background in some modes and also provides the foreground colour for the 640 by 200 2-colour mode. Then finally we need to change the memory map, so the I/O port decoder here is now going to be in the CGA video range, but we're also going to need to have the palette for the digital analog converter here also mapped to here. So I need to modify the BIOS to initialize not only the palette for the monochrome display adapter but also the CGA adapter. So I'm probably going to break the video here because we've already gone up to probably half an hour or so. And so what I'm going to do in the next video, I'm actually going to start laying out the breadboards for the CGA video controller here. So it looks like we're going to need 5 boards across and then perhaps 1 board down the bottom there. So I'm going to be going through in the next video the components and laying out the breadboards and sorting out the chip labels. We use chip labels to go on all these chips just to make things a bit clearer when wiring everything up. And then we'll start to wire it up, and then when future videos we'll then go on to test it. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe, and if you can hit like as well, it just helps to make the videos available to a wider number of people. There is a playlist at the end of the video here. If you go to the playlist, then you can actually go through all of the videos in sequence if you want to actually see how to build the entire PC, starting from a very basic CPU being clocked with no operations all the way up to running MS-DOS. Thanks for watching.